All right, today we're tackling something pretty mind-bending. We're looking at a brand new theory for nuclear magnetic resonance, or NMR. The source we're digging into says the standard explanation, the one from quantum mechanics that's been around for decades, it might be all wrong. Instead, it offers up a purely mechanical one. So yeah, let's get into it.
So why should you even care about something that sounds as complicated as nuclear magnetic resonance? Well, I'm willing to bet you've actually come across it. Ever had an MRI? That's it. The M and the R in MRI literally stand for magnetic resonance. So that incredible technology that lets doctors see inside your body, no surgery needed, it all runs on the very same physics we're about to take apart and look at in a totally new way.
Okay, so what is NMR, officially? The textbook definition goes something like this. You take some atomic nuclei, stick them in a super strong magnetic field, and then you blast them with a radio wave at just the right frequency. When you do that, the nuclei start to, well, resonate. They vibrate and send back a signal that we can pick up. And that little signal, that's the magic behind every single MRI image.
So here's how we're going to break this down. First, we'll look at what the author thinks is fundamentally wrong with the current theory. Then, we'll get into their big idea, what's really causing the resonance. We'll even walk through a visual model to see it in action, check out how the math gets a complete overhaul, and finally, zoom out to see what this could mean for, well, all of quantum mechanics.
All right, let's start with the problem. According to the theory we're looking at, the standard explanation for NMR isn't just a little bit off. It has a huge logical hole right in the middle of it.
And it all comes down to this one little word, intrinsic. See, current physics says the resonance is caused by nuclear spin. But they also say the spin is intrinsic, which is a fancy way of saying the nucleus isn't actually spinning like a little planet, it's just a property it has. The author of this theory looks at that and says, wait a minute. If it's not a real physical motion, then it's just a mathematical idea. It's not real.
And that's the big question that this whole new theory is built on. Think about it. A radio wave is a real thing, right? You can measure it. The resonant signal that comes back is a real thing, too. Doctors build entire images from it. So how can a real thing, the radio wave, interact with something that's not real, the intrinsic spin, to produce another real thing? It's a paradox.
So here's the showdown. On one side, you have the mainstream view. Resonance is caused by this abstract idea of intrinsic spin. On the other side, you have this new theory that says, nope, forget the abstract stuff. The resonance is caused by something totally real and physical, electrons actually moving around.
Okay, so if it's not the intrinsic spin of the nucleus, what is it? What's actually vibrating? Well, according to this new idea, the answer has been right under our noses the whole time.
The central claim is pretty radical. It says we've been pointing our finger at the wrong culprit. It's not the nucleus doing the resonating at all. It's the electrons. And not just any electrons, but very specific ones orbiting at the top and bottom poles of the nucleus.
But wait, right? How can a teeny tiny electron possibly resonate with a radio wave that can be a meter long? Well, this is where the sheer power of an MRI machine comes in. The theory goes that the machine's magnetic field is so incredibly strong that it whips these electrons up to nearly the speed of light. And when that happens, thanks to relativity, the electron's own wavelength gets stretched out a lot. It scales up until it's in the same ballpark as the radio wave, around a meter long.
Okay, I know this is still pretty high-level stuff. So let's bring it down to earth with a really cool visual example from the source material. We're going to use two different types of oxygen to see exactly how this whole mechanical idea is supposed to play out.
So we're looking at oxygen-17 and oxygen-18. Here's the interesting part. Oxygen-17 shows up in NMR scans, but oxygen-18 is invisible to them. Why? This new theory claims that the physical difference between them is the key to the whole puzzle.
Okay, so let's break down this model of oxygen-17. The black disks are protons, the green circles are neutrons. Pretty standard. But the really important thing to see here, for this theory, is how lopsided it is. See that lone neutron parked right at the top pole? And notice how the bottom pole is totally clear?
Here's the punchline. That neutron at the top is like a roadblock. It gets in the way of the electron that would normally be orbiting there, effectively silencing it. But down at the bottom pole, there's nothing in the way. The electron there is free to orbit as it pleases. And it's that single freewheeling electron that's able to sync up and resonate with the incoming radio wave.
And now look at oxygen-18. This solves the mystery of why it's NMR inactive. It has one extra neutron, and where does it go in this model? Right to the bottom pole. So now you have roadblocks at both poles. The top electron is silenced, and the bottom electron is silenced too. There's nothing left that's free to resonate. And just like that, the whole atom goes dark on an MRI scan. So, the physical model makes sense in a mechanical way. But what about the math? You can't just propose a new model without new maths to back it up. So next, we're going to look at how the author takes on the most famous equation in this field, the Larmor equation. So this is it, the Larmor equation. It's basically the heart of traditional NMR physics. Its whole job is to tell you the exact frequency, that's the omega symbol, you need to use to make a nucleus resonate. And it uses things like the strength of the magnetic field, B. But it also uses this other thing, G, the G factor. And that little g is where this new theory says all the problems are. The whole argument against the old math is focused on this G factor. The author points out that even mainstream sources admit these G factors aren't really calculated from some deep theory. They're measured in experiments. So, from the author's point of view, that makes it a fudge factor. It's not a number that predicts a result, it's a number you plug in after you already know the result just to make the math work out. So what happens when you throw out all the stuff the author calls fudge factors? The G factor, the magnetic moment, even pi. Well, you're left with this, a new equation that is just shockingly simple. All it says is that the wavelength, lambda, is based on the electron's radius and its velocity. That's it. And this is the mic drop moment for the theory. When you take that simple equation, plug in the known radius of an electron, and set the velocity to the speed of light, which is what you'd expect in that powerful magnetic field, what do you get? 1.0098 meters. That is almost a perfect match for the actual radio wavelengths they use in real-world NMR machines.
And that brings us to our last section, and really the biggest takeaway from all of this. Because what we're looking at here isn't just a new idea about NMR. If this theory is right, it's a direct challenge to the way we think about quantum mechanics as a whole.
The argument is this. If you can explain things with a simple, physical, mechanical model, then why do you need all the abstract, complicated stuff from quantum mechanics? Concepts like intrinsic spin, magnetic moments, the moment of inertia, even things like pi and motion equations or the fine structure constant. This theory suggests they might just be overly complicated workarounds for a reality that's actually much, much simpler and more mechanical.
So we're left with this one really big question that this whole idea forces us to ask. What if the quantum world isn't this weird, spooky realm of probabilities and abstract concepts that we can only describe with math? What if at its core, it's a world of real, physical gears and levers, a world of purely mechanical interactions that we can actually visualize and understand? It's a fundamental shift in perspective on what reality itself might be.